Hi everyone, this is Jolith ONeilDunne with the University of Vermont, and I'll be presenting our work on tree canopy assessments, planning for a greener future, with techniques we've developed in collaboration with the U.S. Forest Service. So for years, we've been using remotely sensed data to map and better understand our communities. We typically map things like roads, parcels, crime, buildings, and even parks, and we tend to manage what we can measure. What we generally haven't done well is mapping our green infrastructure, and it's incredibly important. It's useful for recreation, helps us address key issues like the urban heat island. Tree canopy reduces stormwater runoff, and we're seeing cities throughout the United States invest in their tree canopy to help them chart a greener future. As communities embark on these green initiatives, they have a lot of questions that they cannot answer because of the lack of information. For example, how much room do they have for new trees? How much tree canopy do they have in the first place? Then how does tree canopy relate to other factors so that they can address issues such as providing more ecosystem services, maybe reducing the urban heat island, or addressing issues of environmental justice? Now, in order to make these decisions, they need accurate and detailed information so that they can make the type of decisions that will help their cities more sustainable and more economically robust in the future. And this all starts with mapping. And thanks to advances in remotely sensed data, such as LiDAR and high-resolution imagery, we finally have the ability to map each and every single tree in the city. Our techniques, which use a combination of object-based feature extraction, artificial intelligence, and manual editing, integrate LiDAR data with imagery to derive not just tree canopy, but land cover data with more detail and more accuracy than ever before. And we've carried out these projects throughout the United States, from major cities on the East Coast, such as New York City, to semi-arid environments, like in Los Angeles. And once we produce this land cover information, we can fuse it with other geospatial data to provide actionable insights so that these communities can help to increase their tree canopy and chart a greener future. Some basic questions like who owns the trees? Well, with our land cover data, we can combine it with land use information to understand who is the majority stakeholder as we seek to preserve and increase our tree canopy. In this particular community, you can see that the residents are clearly the dominant owners of the tree canopy, but in addition, the rights-of-way, the institutional, and even other types of land uses are also important. This helps communities understand where they can control tree canopy initiatives, such as in the rights-of-way, and where they have to rely on other stakeholders in outreach campaigns, such as in the residential and commercial areas. By integrating LiDAR data, we can understand the tree canopy height distribution. We can map the crowns of individual trees, extract the detailed height information, and use this as a proxy to help understand the age distribution of the urban forest. We've developed algorithms that help understand the patch class. These are useful because we know that larger forested patches provide increased ecosystem services, especially when it comes to wildlife habitat. And of course, we know that being in the shade of a tree is more than just being under the shade of a tent. Trees transpire data, and through this evapotranspiration help to keep us cool. So we can integrate our tree canopy data with other information, such as urban heat island data from the Landsat satellite, to actually show the types of ecosystem services that trees provide. We can integrate it with census data to see if there's an equitable distribution of tree canopy. This helps us understand how tree canopy relates to issues such as environmental justice. For example, our work in Los Angeles, in which we integrated the tree canopy data with census block groups, shown by each one of these squares here, which each square representing the percent of the city's tree canopy within each census block groups, we see that the tree canopy is highly concentrated in a very few census block groups that are in the wealthiest areas of the city. We can run correlations between tree canopy and median household income to see if richer residents are benefiting more. By integrating property parcel data from the assessor's office, we can see the effect that housing age may have on tree canopy. For this community, we see that properties that were recently constructed generally have lower tree canopy amounts because trees and new construction rarely mix. We've been working with our colleagues at the University of Vermont Complex Systems Center to integrate social media data to see if green spaces influence happiness. And it turns out that we can tell from social media posts that when people are in greener areas, they tend to be much more happier. Happier people tend to have better health outcomes and even can perform better in their jobs. Most recently, we've been integrating decades of remotely sensed data to help communities understand how their tree canopy has changed over time. For New York City, we brought in their imagery and LiDAR data from 2 time periods, and working with collaborators in the city, AppGeo, and Quantum Spatial, we're able to produce the most detailed accounting of the tree canopy change over this 7-year period. In doing so, we mapped trees that hadn't changed, we mapped new trees and tree canopy gain, and also those trees that were lost. This helps decision makers understand the dynamics of the urban forest. It also helps them understand some of the drivers of tree canopy gain and tree canopy loss. By overlaying the data on top of the 2017 LiDAR, we can see that the loss areas have clearly been removed. They no longer appear rough. Yet we see also additional tree canopy thanks to natural growth and plantings that shows up. Then we also can understand what hasn't changed and remained stable over time. By bringing in this data over larger areas and aggregating it to grid cells or hexagons, we can understand patterns throughout a community. In this particular case, we see northern areas of the city that have experienced a decrease in tree canopy, where southern areas of the city experience gains. And a variety of factors play into this, from real estate prices to individual residential decisions, to land ownership, to zoning regulations. Summarizing this information in charts helps us understand that it's not simply a matter of aggregate gains and losses, but in different land uses, we see different amounts of gain and loss. And these decisions, once again, are driven by a multitude of factors. And these charts and graphs provide insights, letting us know how conservation practices help to improve tree canopy over time, but that individual landowner decisions, such as buying small properties, removing those houses, and developing larger homes on them, results in higher amounts of loss. Once again, by fusing this data with the LiDAR, we can gain a better understanding of the tree height classes that are contributing the most gain over time. In this particular graph, you can see for this community, trees in the 10-foot to 40-foot class are contributing most of the new tree canopy. When we take a look at the heights of the trees that were lost, we see an alarming pattern, and that is that trees in the similar height classes are also the ones being removed. The end result for this particular community means that those trees that are most productive in adding new tree canopy are also the ones that are being removed. If they can retain these trees over time, they'll have increased tree canopy, more ecosystem services, and better outcomes in a number of measured areas. If you'd like to find out more about tree canopy assessments, please visit the U.S. Forest Service's Urban Tree Canopy Assessment site, or feel free to reach out to me via email. Thanks for listening, and have a great virtual conference.